Okay? You are basically bringing this down in front and then subtracting. True? So now when we integrate, that means we're going from a derivative, doesn't necessarily have to be the first derivative, just a derivative, to the previous function. So in this case, I'm just going to say the first derivative to the original. We're basically going backwards. So here we would bring this down in front and subtract 1. Okay, that was the order of the steps, right? So now we literally have to go in reverse. Meaning when we are integrating f prime of x, which we're going to get plenty of practice, but I just want you to see, this was just with a function. No trig, no nothing. We literally have to go exactly backwards, meaning when we take the derivative, we start with the power and bring it down in front. We're not doing that. We have to go backwards because the second step was to subtract 1 from this. So if we're subtracting to take the derivative, what are we doing to take the integral? We're going to add 1. So that means this would be x to the 4th power, true? Okay, we're adding 1. So this has a coefficient of 4. So when we brought this down, whether there was a number in front that was visible, which in this case it is not, it's 1, right? We were multiplying 4 times 1. So if this was a 3, it would be 4 times 3. Instead of multiplying, what do you think we're going to do? We are going to divide, and we're now going to divide by this. So we're going to divide by 4. Okay, we're going to do it again with this one. So we have minus, and we'll put the coefficient here. We'll simplify everything at the end. We add to our exponent first. So now this becomes x cubed. And you divide by the new exponent. Okay, so this is plus 10x to what power?
2.
Yes, second power, and I have to divide by that 2. Okay, so really, we took the derivative of our original. We essentially got the velocity, right? First derivative. Now we're going back to the original. So when I simplify, this is x to the 4th minus 2/3 x cubed plus 5x squared. What's missing? The constant. So here we could write minus 3 because we knew what the constant was. When you are given an integral like this, okay, if I ask you to integrate this, you have no idea what the constant is. Okay, but you need to cover yourself. The constant could be 5, it could be negative 10, it could be 100, it could be 0, still constant, so you need to write plus c. Whenever you integrate, plus c. Okay, you basically are saying, there's a constant there. I currently, with the indefinite integral, I don't know what it is, but I'm just saying, just to cover myself, there's a constant there, I just don't know what it is, so I'm putting a placeholder in its spot. Does everybody understand what we just did? We're going to practice this procedure again, but I'm just showing you we are moving in the opposite direction from the derivative. Questions? Everybody okay? For now? Okay, so there are a series of things that we do need to cover first, and in addition to that, we will talk about some integrals that you will need to commit to memory, which is essentially basically just taking your derivative flashcards and flipping them over and going backwards. And don't forget your plus c. Okay? Let's talk about the definition. So first of all, we're going to talk about the indefinite integral. We will eventually get to the definite integral. And this is where it will take us back to the area under the curve where we practice with the Riemann sum. So here our definition is, if we are given a function which they have renamed capital F, and we call it the antiderivative of a function, little f. So that means this is the derivative, right? Okay? This is the original. On a given open interval, then we're saying if we take the derivative of this, this is what we get. All right, now they're just renaming, and again, this is just in general terms. So when you see it in specifics, for some of us, it might make more sense. So here they have a theorem. They're saying that if capital F of x is any antiderivative of f of x, so they're distinguishing between the two. That's why they have one capital, one lowercase. Okay? On some given open interval, and for any constant c, this is what I talked to you about when we practiced. When you take the integral, you have to write that plus c. You're just covering yourself saying that there could be a constant there. And you have to indicate that. Eventually, we will figure out what it is when we go into the definite integral. Okay, and it says also an antiderivative. This is also an antiderivative on that interval. Each antiderivative or integral, because this is just such a long word, of f of x on this interval can be expressed in the following form. Okay, and this is what we're expecting. You will choose the appropriate c value when you are given boundaries. An indefinite integral has no boundaries. We're just giving a general. Just like if I were to ask you to take the derivative of the sine of x. I'm just giving that as an example. But then I might say to you, find the slope at x equals, I don't know, pi over 3. So the slope means take the derivative and evaluate it at a specific value, right? When we take the integral or the antiderivative, we're going to find that c value. Okay, and I'll show you how to do that later. So we have a process of finding the antiderivative, and it's called antidifferentiation. Guys, I never say that because it's just too much. I will say integration. Okay, so this is integration. You're going to take the integral. You may see antidifferentiation in directions. These terms are interchangeable. Okay, so for the first one, they're saying take the derivative of capital F of x, and it's going to give you f of x. Again, distinguishing between the two. Then, integrating the function f of x produces an antiderivative in the following form. Meaning, this is just by definition. If this says d dx, it means take the derivative with respect to x of the given function, and they're saying this is the result. So this right here is the derivative. Does everyone understand that? So then the antiderivative is going backwards to the original function, but again, you're covering yourself with the plus c. You don't know what the value is, but you're saying it could be there. Everybody good so far? Okay, the notation can get a little tricky, but it's not really that bad. So in the first one, you have the integral. Remember, we talked about this with the Riemann sum. What does that mean? Area under the curve, okay. The integral of f of x dx is going to be capital F of x plus c, where c is understood to represent any arbitrary constant value. Okay, so it's just important to note that 1 and 2 are just different notations. Okay? So then here, this is how you could express these in different ways. So if you're asked to integrate x squared dx, meaning go backwards, find the original function, it's the same thing as saying take the derivative of the original. So here, if I take the derivative of this would be what, 3x squared? Right? And then 1/3 times 3, that goes away, so that gives me the x squared. If c is any constant, 5, 7, 11, 33, -1, what's the derivative of a constant? So that's where you are. Does that make sense? Okay, so these are equivalent. Okay, this is going from the derivative to the original. This is taking the derivative of the original and going to the derivative. All right. So here we have the adjective indefinite. And basically what this means is that your result is going to be a generic function. All right. So I'm going to show you an example, and we're going to take a look. What is the equation for that function? Okay, so this is y is equal to x squared. Whoops. What is the equation for this function, if I can get it drawn? Yep, y is equal to x squared plus 2. What's this one? Okay, you guys are getting the point? All right, so now if I said to you, take the derivative, which I'm just going to use a regular pen, take the derivative. We have y is equal to x squared plus 2. What's the derivative? 2x. y is equal to x squared. What's the derivative? 2x. Y is equal to x squared minus 1. What's the derivative? Okay, so do you see they're all the same? So even if you write a plus c, it's a generic form of that function saying it could be any variation of that. Okay, but you need to indicate that there could be a constant there. That way when we do find it, we can distinguish amongst the, in this case, 3 versus between any others. All right, so what we have is this notation here. The elongated s is known as the integral sign. Okay. If you have a square root, what is the thing underneath the square root called? Yeah, the radicand. Okay, the function f of x, okay, which is beside, because it can't really be under the integral, is known as the integrand. But it's real. Okay, and c is known as the constant of variation. Constant of variation. That's hilarious. Okay, so if an independent variable other than x is used, you just need to make sure, yes, sure, just for you. If an independent variable other than x is used, meaning you can use any variable for a function. You can use theta, you can use t, you can use m, j, k, whatever you want. Typically, we will use x or theta. You just need to change your notation. So, for example, this is s of t. You got to make sure this is dt. Okay, you can't have s of t dx because that doesn't make sense, especially when you're talking about the integral. Here you have theta. Here you have u. Okay, so just make sure that the notation is appropriate. And then the last piece here that I just want to talk about before I go through some specific theorems. Sometimes, if you are taking an integral of like 1, okay, it will be absorbed into the notation of dx. So you won't always see the problem like this. You might see it like this. If it makes you feel better to write the 1, then write the 1. This is the one that I typically pull apart, especially too if you are integrating and you would need to bring this to the top. You might see it like this. I would pull it apart. I would get in the habit of pulling it apart because I'm going to show you the process for dealing with integrals like this. So this is the way you would typically see it, especially in the book, or sometimes like if we're on AP Central or whatever. Okay, you might see it there. Okay, in AP Classroom. So it just depends. So this is what you would typically see, and you need to pull it apart like this. Okay. So these are in the concept cards, just so you're aware, for those of you that haven't gotten started yet. Integration formulas, you need to know them. Okay? I think the most important ones were put on there. So for example, this right here, this left-hand column in both sections is your differentiation formula, meaning when you take the derivative of x, you get 1. So now we're going backwards. So these are all the integration formulas on the right-hand side. And what this is saying is if you integrate dx, meaning it's 1, the integral of 1 is x plus c. So you definitely need to know that. This is the most important formula here. Typically, we're going to use, you're going to see n. I think it's teeny tiny, and I know it's hard to read, but they're using r. And this is what I showed you in that first problem. So what this is saying is if you are integrating x to the r power, you're going to add 1 to that r and then divide by r plus 1. I like to think about it as multiplying by the reciprocal, especially when you have a coefficient. Okay, because when people, if the coefficient is a fraction like 2/3 instead of 3 or 2, people will leave it as a complex fraction. You cannot leave your answers as a complex fraction, and I'm sure we're going to see plenty. So if you don't understand what I'm talking about, I'll get more specific in a minute. These are all your trigs, meaning basically you need to be able to go backwards. So you have the integral of the cosine, okay, all the way through up here, number 8, which is the integral of cosecant cotangent. So again, this is essentially, you're asking yourself, what do I take the derivative of to get this answer? That is what you're saying. Okay, so you definitely need to know all of these. Are you going to remember them right now? Not necessarily. Yes?
How does it work for derivatives that use the...
We don't have a chain rule. I'm going to talk...
Not the chain rule, the like multiplication one.
I'm going to talk to you about that in just a minute, but that's a good question. We do not have a product or quotient rule. So Zach asked a really, really, really good question, which I'm going to get to when we do some of the problems. So if you notice on here, we do not have any product or quotient rules. It's because there aren't any. Basically, we will cover eventually what's called U sub, and that is undoing the chain rule, which helps with the product rule, but there is no quotient rule. So you will literally have to divide. And I'm going to show you. Okay? So our favorite, e to the x, still e to the x. Here, everything is backwards if you're dealing with b to the x dx. 1 over x. This is a very specific case. The integral of 1 over x dx is equal to the natural log of the absolute value of x. I'm going to show you why using the rule doesn't work, meaning you add 1 and divide by that new exponent. And people get caught up in there. This is one you definitely have to know. Okay? And then your inverse trig functions. Here, this is the integral of 1 plus x squared. It's our inverse tangent. Remember I told you that inverse tangent and inverse sine are the most common ones that you'll see. So here's inverse sine. This one, rarely ever seen, secant. But it's there, so you need to make sure you know it. Probably not as well as these two. Okay? I would star these two and kind of meh this one.
And what about inverse cotangent?
Nope. Okay, so what's on here? And these, like I said, these are on the concept cards.
Yeah.
So these are the integrals that you definitely need to know.